Hi everyone, and thanks for joining us today. My name is Charlotte Argue, and I'm the Program Manager for Climate Change and Air Quality Program at the Fraser Basin Council. We're a non-profit organization based in British Columbia, and we're a partner of the West Coast Electric Fleet Initiative. So this is our second West Coast Electric Fleet webinar of 2016. The topic today is the power of charging stations, smart systems for the future. So thank you everyone for joining us today. Before we get started, I'll just go over a little bit of admin around this GoToWebinar. So everyone should be hearing me either through their telephone or through their mic and speakers. So you can be using your computer or the phone. Using your phone, there's a PIN number and a dial-in code to call into. If you have any audio issues, you'll probably not be able to hear me now, but we do have a chat box where my coworker can help you out. So if you are experiencing any issues, please just chat in the chat box there. We're going to have everyone on mute today. So if you do have questions as we go through the presentations, please do use that question or chat box to pose your questions. As we go along, we will try to get everything answered between the presentations, and also we'll leave some time at the end to go through questions and answers as well. So today we have two presenters, Jeff Turner and Clay Howie. Before I turn it over to them, though, I'm just going to take a few minutes to cover what the West Coast Electric Fleet Initiative is. So it's an initiative of the Pacific Coast Collaborative. It's in response to their action plan on climate and energy, which is the image you see before you. This is an agreement between the states of California, Oregon, Washington, and the province of British Columbia. And it's really put together to support collaborative action in the areas of climate and energy. One of the goals of this climate action plan is to take action on or take actions to expand the use of zero-emission vehicles, aiming for 10% of new vehicle purchases in public and private fleets by 2016. So this is a fairly ambitious goal, and the West Coast Electric Fleet Initiative was formed to help fleets navigate this goal and help fleets transition to zero-emission vehicles themselves. So we have a steering committee and an implementation committee full of great partners. That includes members of the 4 jurisdictions, as well as several Clean Cities coalitions, CalSTART, Drive Oregon, Ross Strategic, others, including ourselves at Fraser Basin Council. We also have over 30 partner fleets who are members, and that includes local and state fleets. You can see the list here. It includes private companies, utilities, and others. They span the West Coast, and they also range in size of fleet as well. To become a fleet partner, it's free. All that's required is to demonstrate your commitment to zero-emission vehicles by signing our pledge. So the pledge has 3 tiers, and this is to reflect different stages a fleet might be at for electric vehicle adoption. And we encourage anyone who hasn't already signed on to this pledge and become a fleet partner to do so. It's all available online on our toolkit. I have the URL for the toolkit there. It's westcoastelectricfleets.com. And this toolkit also hosts a number of resources and tools, including business case calculators for electric vehicles, information about region-specific programs and incentives, as well as a number of case studies where we profile certain fleets across the coast to show what they've done with procuring electric vehicles and the successes that they've had to date. So I think one of the most valuable aspects of this program is the peer-to-peer network for sharing best practices and lessons learned. And that's part of the reason why we do these webinar series. There were a number of webinars in 2015, and again, this is the second for 2016. All of these webinars have been recorded, and you can access them on the toolkit as well. So if you missed any of the webinars, you can go back and watch the recording. So with that, I encourage you again to join West Coast Electric Fleet if you haven't already done so. Again, there's no cost to signing up. And I'd like to now introduce our first speaker. I'll just get my colleague to switch over to presenting. And meanwhile, I'll introduce you to Jeff Turner. So Jeff is an engineer with Advanced Transportation Department at Powertech Labs, which is a subsidiary of BC Hydro, the main utility in the province of British Columbia. Jeff's work focuses on electric vehicles, charging infrastructure, and grid integration. Before joining Powertech, Jeff worked on the Ford Transit Connect Electric at Aerodynamics, and he's also worked at a number of electric and hybrid snowmobile prototypes during his studies at McGill University. So Jeff, over to you, and thank you for joining us.
Great, thank you, Charlotte and Ryan, for the opportunity to speak. I'm assuming that everybody can hear me. If not, I'm sure somebody will chime in and let me know. But so as Charlotte explained, I work at Powertech Labs, and we're a subsidiary of BC Hydro, so that's the main government-owned electric utility company here in BC. And so they spun us off about 30 years ago, and we do work in a number of sort of clean tech. Sorry, I think I might have some auto advance going on here. Classic. Mistake here. Use timings. Turn that off. Great. Sorry about that. So yeah, we do a lot of work in the utility industry. We're doing research and development, testing and consulting related to the utility industry and others as well. So we've got a campus out in Surrey, BC, which is a suburb of Vancouver. And a number of different labs, high voltage labs. We can simulate lightning and all sorts of cool things like that. But my work has sort of spun out of the group called Smart Utility Technologies. And this is where we're looking at a number of emerging technologies that utilities are looking to sort of optimize delivery of electrical energy to their customers. So for example, this is our outdoor testing lab. It's a 25 kilovolt distribution yard where we can test things out like the self-healing grid, the ability to identify faults and isolate them and restore power more quickly. This is some of our indoor infrastructure, where one of the key aspects of a smart utility is the communications aspects. So we have a replica of BC Hydro's smart meter infrastructure, all the communications from the utility back office down to the smart meters on the homes. So in this environment, we're really able to test out a bunch of emerging technologies. And for us, we really saw EVs as a great opportunity to pilot a number of key smart grid concepts. So it's a significant new load for the grid, but it's also potentially a flexible load. And it's also, interestingly, a nomadic load that might move from one part of the grid to another throughout the day. But we've actually been doing EV work at Powertech Labs for a number of years, even as far back as some of the earliest public charging station installations in the region. We were doing that kind of stuff, but we've been really excited to see it become more and more of a mainstream thing as EVs become more and more common. So it's been important for us at Powertech to make sure that we're making the most of our facilities and our expertise and staying on sort of the leading edge of new technologies as they emerge. So in particular, a lot of work around DC fast charging and grid-connected smart charging systems that we'll talk a little bit more about later on. But just to start, let me just lay some groundwork in terms of the definitions and things like that. Some of this might be familiar to you, but we definitely want to make sure that anybody who's new to the world of electric vehicles has a good foundation. This is a diagram that I like to use from the Electric Power Research Institute with sort of 4 examples of typical types of vehicle powertrains, starting with a conventional gas-powered powertrain on the left side and all the way through to a fully electric battery electric vehicle on the right side. And I want to bring this up because in between there's sort of 2 intermediate stages and it's important to sort of draw the line here. So the second from the left, that's what we know as a conventional hybrid vehicle. So we're familiar with those. We've seen Toyota Priuses for about 15 years now. And so the important distinction to make here is that while it does have an electric motor and a battery, there's still only one source of energy for a hybrid electric vehicle. The battery and electric motor help make the most use of the gas that goes into the gas tank, but the gasoline is still the only source of energy. Contrasting that with the plug-in hybrid, second from the right. So that's a hybrid electric vehicle where it has a much larger battery and it has the ability to plug it in so you can charge up on electricity from the grid. And that enables a much greater distance in electric mode driving and potentially enough to do your daily driving without burning any gas at all. So I really like to sort of combine those last two categories because from my perspective, whether it's a pure electric vehicle or a plug-in hybrid, they still have similar benefits, but also the same implications for the grid in terms of delivering energy to those vehicles. Some people refer to those collectively as plug-in electric vehicles, PEVs, but in conversation, I just casually refer to them all as electric vehicles, and I might use the term battery electric vehicle if I really mean to refer to a pure electric car. So just to sort of break that down, I won't be talking about hybrid electric vehicles, and also on the right side there, you can see fuel cell electric vehicles. Powertech does a lot of work in that field, but that's out of scope as this discussion because we're really focused on things that plug into the grid. Just to give a few examples that you're probably all familiar with at this point, they're more and more common on the road. These are pure electric vehicles. The Nissan Leaf is probably the most common, but of course we've all heard a lot about the Tesla Model S as a more expensive vehicle. No real secret sauce there in terms of how it gets the sort of 250-mile range. They just simply use a much larger battery that's integrated into the floor of the vehicle. And we've seen a number of battery electric vehicles that sort of match the Nissan Leaf specs, similar like the Volkswagen e-Golf and the Ford Focus Electric. A couple examples of plug-in hybrids. Most of you are probably familiar with the Chevy Volt. GM has sort of struggled with, how to market this thing and advertise it. They landed on the term extended range EV to really highlight the fact that as far as plug-in hybrid goes, this one really offers full electric performance for a significant range up to about 50 miles before the gas engine takes over. Similarly, the BMW i3 is available as either a pure electric vehicle, or you can optionally add a range extender engine. And again, this will allow you to take it much further distances once the battery runs out. I've left the Toyota Prius on there. It's currently on hiatus, but will be coming back shortly. It was just announced at the New York Auto Show. But this really shows as an example that while we're familiar with the regular Toyota Prius, Toyota has offered a plug-in version of it with a much larger battery, and that actually offers a significant amount of electric range, and this will only increase for the next version coming out in next year. A few important trends are coming down the pipeline. Obviously, we've all heard about Tesla's Model 3 coming out sometime at the end of next year. GM has been really happy to remind people that their similarly priced Chevy Bolt will be available at the end of this year as well. And so it's really a trend that we're starting to see, and Nissan is expected to follow with their next-gen Nissan Leaf at the end of next year. Another important trend, and this was included in the poll that Charlotte sent around, you'll see the Mitsubishi Outlander up on the top left. We're finally starting to see some larger plug-in vehicles. And you can tell that a lot of these are sort of higher-end luxury vehicles, but there are a few that are starting to come down the pipeline that will sort of offer plug-in capabilities in a larger format vehicle, including the Chrysler minivan on the bottom left there. And of course, those are all passenger vehicles, but there are also a number of commercial vehicles available. The electric bus segment is really starting to take off. And here in Vancouver, the city of Vancouver actually operates a number of these plug-in hybrid bucket trucks on the top left there that are able to operate the bucket without idling the engine all day long. So that there's really a diverse range of products available now. So that's a good baseline in terms of the vehicles themselves, but obviously we're here to talk about charging infrastructure. There's three main categories of charging stations. Two of them are AC charging stations where you provide AC power to the vehicle and the vehicle converts that to DC using the onboard charger. Either level 1 charging at 120 volts or level 2 charging, which is the most common that we see in public charging contexts. And that's the type of thing that'll charge a car in say 4 to 8 hours. And then at the bottom, some people still refer to this as level 3 charging, but the real distinction here is that this is DC charging and that you're providing DC power directly to the battery on the vehicle. And that allows the charger, which is built into the station, to be much larger and more powerful. And that's what will let you charge up, for example, a Nissan Leaf will charge up to 80% in about half an hour. Here in BC, we've had a number of interesting programs that have really helped to deploy a lot of charging infrastructure with funding from the BC government as well as Natural Resources Canada. So for example, the Fraser Basin Council was responsible for a program that deployed about 500 public level 2 charging stations. Meanwhile, BC Hydro is just about done deploying 30 DC fast charging stations across BC. So it's really led to a great environment for EV adoption here in BC. This is from chargehub.com, a map of charging stations in the lower part of BC. And so you'll recognize orange markers as DC fast charging stations. And for the folks down along the West Coast, it's been great to see that we now have a pretty robust fast charging infrastructure all the way down the coast at this point. Just a couple examples of fast charging stations around BC. Powertech played a role in installing some of the first ones, but more recently we've sort of focused on testing of new types of charging stations that we're looking to use here in BC. So that's one of the more recent dual standard charging stations that can support a wider range of types of vehicles. And it's continuing to grow from there. So there are a number of new programs that are being put together as we speak. So on this map, you can see the green markers. That's the phase 2 deployment of DC fast charging infrastructure that's being planned in BC for an additional 25 fast charging stations to be added to the existing 30. Meanwhile, the Fraser Basin Council is also responsible for a program that will support level 2 charging infrastructure in multi-unit residential buildings. So that's really important. So this has really led to a great environment for EV adoption. We now have over 3,000 EVs on the road in BC. And from my parent company's perspective, that really increases the urgency to start to look at how do we support EV infrastructure and help to minimize the impact of this additional load on the grid. And that's really where Powertech is focused throughout this project, sort of the umbrella project being called the BC EV Smart Infrastructure Project. So in terms of smart grid integration, that really revolves a lot around communications. So it's important to establish a certain degree of communications with charging infrastructure to make sure that we're able to minimize the impact of charging loads on the grid. And so one of the first steps that we took in this direction was to make sure that for all those hundreds of charging stations that are out there, let's at least make sure that we're collecting usage data from those charging stations so that we can understand how much are they being used, which ones are being used more than others, and what are the associated grid impacts with that charging. So this is a system that's collecting data from multiple different networks of charging stations. You can see the 4 different networks on the bottom right corner there. And we've got about 450 charging stations collecting data there. So, but meanwhile, we really want to look to the future, and so we've been looking at new technologies in the lab that can help to not just collect usage data, but also help to minimize the impact of charging on electrical infrastructure. So this is a great diagram that was produced actually a couple years ago, so some of the stats might be a bit dated at this point, but this is a look that BC Hydro had into where we're likely to see the most impact in terms of their electrical infrastructure here in BC. And this might vary depending on the utility. So BC, of course, we have a lot of hydroelectric generation. So that means that we're doing pretty good on the generation side. It's a very flexible form of generation. And here, most of the interest is going to be focused on down the stream in the distribution transformers and substations and things like that. So for us to help to minimize the impacts of charging, we want to make sure we have some means of communicating with charging loads. And so this is a bit of an overwhelming diagram, but basically we just got the lay of the land to figure out all the different options for establishing communications. I'm going to just distill this down to a much simpler diagram. And basically what we organize this into is communication pathways that leverage the internet on the left side of the graph. And then utilities are also interested in potentially leveraging their smart metering infrastructure, as they already have communications down to smart meters at individual accounts. So our job was to look at a number of these different options, and this is our EV Tech Park at Powertech, where we were able to install various types of charging stations and test out their ability to control charging in various ways. And I just want to show this as an example. This was a Nissan Leaf that plugged in the afternoon. And this is, you can see where we're inducing load control to reduce charging at certain times. And even with a very aggressive control strategy, we are still able to reach a full charge by 7 a.m. the next morning. And that's really the big opportunity here, is the fact that vehicles stay plugged in for a long time, and there's a lot of opportunity to defer charging to lower demand periods. But as this project has progressed, we've realized that beyond the utility constraints, there are a number of electrical constraints on the customer side as well. And in some of those cases, you don't necessarily need to rely on this complicated communication infrastructure all the way back to the utility back office, especially with commercial buildings and fleet vehicle charging scenarios where you might have a large number of vehicles charging in one place. So I know a lot of this is focused on communications back to the EV head office, but really there are opportunities to rely on local communications and integration with building energy management systems to minimize charging loads. In terms of our demonstration sites, we're looking to demonstrate some of these technologies in a few places out in the field. And so one of the key use cases that we wanted to demonstrate was workplace charging, where you might have a number of employee vehicles charging in the same place. So this is a photo of BC Hydro's Edmonds complex, one of the main office towers. And here we're working with the fact that the building undergoes peak demand on a very regular basis during the middle of the day. And the big opportunity here is to make sure that when EVs are charging, we avoid charging at the peak time as much as possible. The system that we'll be demonstrating here at the Edmonds facility is produced by Energy Technologies, a company based in Quebec. And they've developed a solution that allows you to manage charging with a group of charging stations according to certain limits. So that might include power sharing, in which case you might be making the most of a limited capacity at your electrical panel to install a greater number of charging stations, or even active power limiting, which might reduce the amount of charging power according to the time of day or based on real-time data collected from the building automation system. And this can really help to minimize the peak demand of the building and reducing associated demand charges from the utility. Another one of our demonstration sites is at the University of British Columbia, where they have a fleet of 10 smart EV electric vehicles operating in their fleet. In this case, we're actually using a system developed by Fleet Karma, the company that we work closely with for our EV cloud data collection system. And they've augmented their interface with charging networks by adding an interface with a vehicle data logger. And this allows them to incorporate vehicle side data. As such, they're able to optimize smart charging decisions based on the needs of the vehicle and the driver. And their system is compatible with both add energy and charge point stations. So in the case of UBC, we'll be demonstrating with the existing 10 charge point stations that they use for their fleet vehicles. So yeah, those are two of the systems that we'll be demonstrating as part of this project. And in all cases, we've had a great chance to test them out here at Powertech in our lab. And we're really excited to roll those out into the field. And over the coming months, we'll be excited to report on the success of these technology demonstrations. So that's all I had to say for today, and I'll wait for you for any questions in the question period at the end of the presentation. Thanks.
Great, thanks so much, Jeff. So if anyone has questions, again, you're all on mute, but what we're going to be using is the question chat box in the drop down on your control panel. We'll save all the questions till the end. So I'm just going to introduce you to our next speaker now, which is Clay Howie. Clay is the technical lead on the Smart Microgrid Research Initiative at BCIT, and he coordinates researchers in the areas of energy management, renewable generation integration, substation automation, smart metering, electric vehicles, and charging stations, as well as demand response. Clay is also an advocate of EVs, and he owns and drives a Nissan Leaf. So over to you, Clay.
Thanks, Charlotte, and hi everyone out there. So just a little bit of background about BCIT, because I know we've got folks from the whole West Coast area. BCIT is British Columbia Institute of Technology, so we're a fairly large post-secondary educational institute here in BC. And just a bit on what we do. So we do research and development, looking for solutions for problems in smart microgrids, critical infrastructure security, and IT, but we're mainly talking about smart microgrids in the context of today's discussion. A bit about how we interact with industry. So BC Hydro is our strategic partner in our smart microgrid research, and in particular the Oasis project that I'm going to be talking about today involves partnerships with Siemens, Panasonic, Schneider Electric, Encompass, and Powertech Labs. We are a part of a network called NSMG. So here in Canada, for the American folks, we have a federal organization called the National Science and Engineering Research Council, called NSERC, and we have an NSERC Smart Microgrid network. So we've got an acronym within an acronym there with NSMG-Net, and that involves BC Hydro, Hydro One, utilities right across Canada and other folks in the smart grid space. So the goal of all of this is to provide a vendor-agnostic test bed for smart grid technologies. We also have IT firms contract directly for R&D services. We've got about 10 research staff that are dedicated full-time to R&D projects. So this is non-teaching faculty that participate in projects. We also do involve students. We've currently got a couple of PhD candidates from McGill in electronic engineering working in our lab, as well as one U of A master's student. And we've had, well, you can read the PowerPoint there. We've had students from lots of different academic institutions across Canada working in our lab. By our NSERC strategic microgrid network, we involve students from universities right across Canada: McGill, University of Toronto, UBC, U of A, Waterloo, so on. But mainly here to talk about OASIS. So OASIS is a project here at BCIT's Burnaby campus. We have about 6 campuses altogether, but by far the largest one is here in Burnaby, BC, which is a suburb of the Greater Vancouver area. So the project was to build a 250 kilowatt solar canopy over a parking lot. It also has a 40-foot container that houses 500 kilowatt hours of lithium-ion batteries, so we can store the energy. And we've got 2 DC fast chargers, 6 level 2 chargers, and a couple of level 1 electric vehicle charge stations, as well as LED parking lighting and some house loads there. So that's what the project actually looks like. I don't have the dimensions of that. We've got roughly a football field size of PV, sorry, I'm using acronyms, photovoltaics or solar panels. So we can generate our own electricity for charging our cars. The entire system is islandable, so we can disconnect from the grid and we can reconnect to the grid. We can backfeed surplus energy that we generate to the grid, or we can take energy from the grid. We can store the energy in the batteries. So the project demonstrates state-of-the-art solar technology coupled with energy storage and the direct displacement of CO2 emissions related to transportation. Some of the other components of OASIS is we've got a reservation system. We've got a kiosk located out in the parking lot right by the chargers. EV drivers can make reservations for a charge. So the system can deliver power based on the availability of solar energy and the destination of the EV driver. We've got an advanced generation and load forecasting system from Siemens. And the idea, as Jeff was talking about, is to mitigate the effect of EV charging on the electrical grid. So, what is the problem that we're trying to address here? Usually I talk about the problem before, but I wanted to give a little bit of context about the bits and pieces that we've got here at OASIS. Here in BC anyway, according to BC Hydro, we've got adequate generation and transmission capacity to electrify BC's fleet of cars, passenger cars. But on the distribution side, we've got some issues. So the issue is that if lots and lots of EVs plug in simultaneously, if everyone's driving home from work and they arrive home at 5:30 p.m. and everyone plugs it at once, then the distribution feeders and transformers might become overloaded. Probably would in certain areas. So what the utilities call it is a solution called demand response. And demand response solutions for electric vehicles need to be researched, tested, and verified. So that's what we're trying to do here. So the OASIS system can do demand response to shave demand peaks and fill in the valley. So the graphic that you see on your screen right now basically shows a weekly profile of electrical demand here at BCIT. And you can see it's very peak. Every day has got a peak, and then every evening is a valley. So, or at least for the 5 days when classes are in here at BCIT, the weekends are obviously less load. So if you can see on your screen the green peak and the blue valley there, that's energy that through using OASIS's energy storage system, we can shave some of those peaks. So that green part is energy that we can supply to the grid to knock that peak down. And we can also charge up those batteries at night when demand is very low. So why is that a big deal? Generation generally isn't nearly as peaked as this. So for example, two of the most common forms of electrical generation throughout the world are coal and nuclear fired generation. Those two methods of generation don't throttle very well. Here in BC, we've got the luxury of hydroelectric dams, and they make adjustments to the spillways every hour on the hour, so they have a better method of matching demand to generation. But most of the world doesn't have that luxury. So this presents a problem when generation is relatively flat and demand goes up and down, and it's very peaked. So there's quite a few strategies to mitigate this. Energy storage is one of them. So more detail on how Oasis does this, moving from left to right on the diagram. We have a weather forecast that we pick up from a feed from the University of British Columbia, and so that's 3 days out. So we can, from the weather forecast, we can make predictions about how much electricity our large solar array is going to generate. We also have a forecast on how many EV charges are going to be taking place, and that's based somewhat on historical data and somewhat on our reservation system. So if we can have an idea of how much energy is going to be generated and how much is going to be used, then we can use our storage system to try and match that as best as possible. So the system in the middle is called DEMS, which is the Siemens system, which takes all of these forecasts and comes up with schedules for when we should be charging and discharging our large lithium-ion battery array. We also, one of our partners was Schneider Electric, that provided 2 of the DC fast chargers, and we got them to customize the control on their charger so that we have a fairly high level of control on charging events. So we can deliver a full charge, we can slow the rate of a charge on the DC fast charger, we can completely stop the charge, so we may charge for just so many minutes and then stop a charge, or we could completely, in an extreme case, when we were islanded from the grid and very little solar was being generated and our batteries are running low, we could deny a charge. And that would likely, again, happen in a staged scenario where, for example, those that have made a reservation, those charge requests would be honored, but people that haven't made a reservation, those might not. This is for research purposes, and it's certainly not something that we would be having in place all the time, but we can do that for demonstration purposes. The bottom right just shows that we've got bidirectional electrical flow with the grid. We can export back out to the grid, or we can take from the grid, or we can be completely islanded from the grid. So one of the questions that we get asked is, how many cars can Oasis charge in a day from solar? And we have to talk about averages because right now we're getting lots and lots of sun here in Vancouver, but certainly we've got our cold, rainy days in the winter when we don't get very much generation at all. So on average, Vancouver gets about 3 sun hours per day, which equates to about 750 kilowatt hours per day average over a year. And the average Nissan Leaf charging session is about 10 kilowatt hours. The average session time is 30 minutes, so theoretically we could support about 75 Nissan Leafs charging every day just from the solar generation. But you got to factor in some house loads, so that number drops to about 50 Leafs. But again, we have some issues with lineups and queuing and getting everyone to come in at a regular rate. That's where that reservation system could come in. Just a diagram about the charge curve. So this is a charge curve for a Nissan Leaf. So you can see the power level when you're first starting for about the first dozen minutes. The energy delivered to the car is about 50 kilowatts, and that starts to drop off over time. So from about the 12th minute to about the 22nd, it's steadily falling. So a lot of people aren't aware of this. When you plug into a DC fast charger, initially for the first few minutes you're getting a full DC charge. Then the charger itself is going to throttle down. It'll start delivering less and less electricity. It's protecting the batteries, keeping them from getting too warm, etc. So at a certain point it actually becomes more efficient to just unplug from the DC fast charger, move over to a level 2 charger. Some of the unforeseen challenges that we ran into during the course of this project. Location selection, we've got about, here in the Burnaby campus, around between 60 and 70 buildings. Very few, well, really none of those buildings had roofs that were engineered to take on the additional weight of a large solar array. So we ended up building a structure over the parking lot, which obviously had some additional costs. It was very welcome because here in Vancouver we get so much rain. A lot of people love being able to park out of the rain and walk out of the rain to get to the campus. Another challenge was the battery module layout. So on that diagram on the top right, that's one of the cabinets inside the 40-foot container, showing the layout of the batteries. All of that was customized by Powertech Labs, the firm that Jeff Turner works for. So that resulted in an innovative rack redesign. A big problem that we had was the noise. So in the bottom diagram, the box on the left houses the power control system, PCS. And those inverters make a loud, high-pitched shrieking noise when they're operating. So a lot of vendors assume that you're an electrical utility, and so this, the noise isn't necessarily an issue if you've got a greenfield substation installation with, that's out in the middle of nowhere with a big chain link fence around it. But in our situation, we are very close to a residential area, and right away we were getting noise complaints about this when it was operating during the day, especially when we had a lot of solar generation. It starts to howl pretty good, so we had to put in a noise abatement enclosure around that box. We also had a bit of an issue with the cooling system, the system that cools the PCS. The fans were making a lower frequency noise that again was bothering some of the neighbors. So we had to get some of that out of the way, but that interfered with our operation of the system for the first year. The last point there is the EV charger power loss. A little bit unique to our situation. When we were going through the transition to island from the grid and reconnect to the grid, sometimes we experienced transients, little hiccups in the power. And the EV chargers, the DC fast chargers, they were sensitive to that, and sometimes we would get in a situation where it would fault a vehicle. And in some cases, it was such that the vehicle could not continue charging, and even when we disconnected and reconnected, it wouldn't charge. We had to take a Nissan Leaf to the dealership to get the fault cleared and so on. So we had to install a UPS so that the system could ride out any interruptions in power. This is a bit of generation data from our solar array. This is from a year ago. So the orange is what we would be generating if back then everything was fully operational. The green was what we were actually getting. And the main reason for the differences relates back to this previous slide where we had noise issues. The neighbors were complaining we couldn't run the system 24/7. Now that we've got all those in place, we are very close to the orange line. We're generating pretty well completely what the system is capable of. These are the major vendors who are involved, actually project partners. So Panasonic was the provider of the solar modules, solar panels, and the 4-quadrant inverter inside the power control system. Siemens, basically they were the provider for our substation automation gear and the DEMS, the distribution energy management system that takes all of the forecasting and really operates the system. And Schneider Electric is a provider of some smart meters, some other electrical components, and the DC fast chargers. Some of the other BCIT EV chargers that we've installed at our downtown campus, we've got 2 level 2 chargers. The Carey building where I work, that top picture is actually my leaf on the left, and one of my colleagues, Kelly Carmichael's, his leaf on the right. We share a level 2 charger at this building. Our Gateway building here on the main campus has got 2 level 2 chargers and 4 level 1 chargers, and then we have a demonstration net zero home on campus with solar panels and geo-exchange and a wind turbine and so on, and it's got 1 level 2 and 1 level 1 charger. We're also involved in consumer behavior research with UBC, University of British Columbia, University of Victoria, and Simon Fraser University, all universities located here in BC. The research that we're doing right now involves the 6 level 2 EV chargers at Oasis. So we're researching EV driver appetite for aligning charging with the availability of renewables. So we found there's a huge difference between what people will indicate on a survey and what they actually do in real life. So the idea is, you know, would people delay their charging until the sun comes out? So we've developed a system where basically a kiosk can manage their charge. They indicate how much charge they need or in time, so I need an hour charge or 2 hours charge. And they also indicate the time when they need their car to be ready. And then the system can autonomously manage their charge, and basically if the sun is, we're not generating enough solar energy, it will delay the charge until the sun comes out. Now if you know, they needed an hour charge and it's now an hour until they need the charge, we will start taking power from the grid. So we make sure that the cars are ready by the time people specify that they need it, but during that time we've got free reign in how much energy gets delivered to their car. So the chargers, the level 2 chargers that we've got there can be throttled, so we can set them to 0, 1, or 7 kilowatts delivered. So some of the future work, we plan to do some improvements to the forecasting system. We've got a pilot project with Powertech Labs planned to demonstrate some utility-controlled charging at BCIT's A-Fresh Home. And we've certainly planned some more collaboration with UBC, SFU, and UVic on behavior change research. And I just want to leave you with this slide here. So this is a graphic that just shows the number of charging stations deployed in Canada. So BC right now leads the way, even though we are not the most populous province in the country. So Ontario and Quebec have much more population than BC, but right now BC is leading the charge here in Canada. I know Oregon is you know, quite far ahead of us. I'm not exactly sure where Washington State is. But I think it does give some comfort to fleet managers to know that BC and the West Coast is pretty serious about the infrastructure. The Canadian federal government has just announced that they are planning to have a Canada-wide network of charging. So they haven't committed to that yet, but they have been making noises that is going to happen sometime in the near future. So that's it for my presentation. My coordinates are on there, and I believe now it's time for questions.
Great, thanks very much, Clay. And Jeff, both of your presentations. It's great to know about the various technology solutions available out there to manage electric vehicle charging as well as the power supply, and things to start thinking about as a fleet as they start integrating more and more electric vehicles into their fleets. What kind of options are out there to really manage that? So I'm going to pass this over to my coworker Ryan, who's taking questions, and I think a few have come in already. So he's just going to read those out to you now. And if you do have questions or any specific questions to your current situation that you want to pose to our panelists, please send those in, and we can get to them as well. We have about 10 or 12 minutes here.
Thank you, Charlotte. Yeah, the first question is for Jeff. The question is, why does charging depend on the electric vehicle and not just the EV charging station?
Sure, that's a great question. So in this case, both the charging station and the electric vehicle will have maximum capabilities. So in the case of the charging station, that might depend on how big a circuit it's attached to. So the most common level 2 charging station, for example, might be on a 40 amp, 240 volt circuit. That's enough to charge at 7.2 kilowatts. But there are some level 2 charging stations that can go all the way up to almost 20 kilowatts. But at the same time, you're depending on the power electronics on the car. So the car is built-in onboard charger. And you might have noticed that on my slides showing a few EVs, I included the stats for what the power capacity of the onboard charger is for each model of EV. And so, for example, some cars like the Chevy Bolt, they can only charge at a maximum of 3.6 kilowatts. So even if it's plugged into a high power capacity level 2 station, that's not going to mean it's going to be able to charge any faster than that. Likewise, if you have a Tesla that's able to charge at about 20 kilowatts, if you're plugged into a more common 7 kilowatt charging station, there's nothing the Tesla can do to pull more than the maximum power allowed by the charging station.
Thanks, Jeff. The next question is for Clay. What's the business case like for a project, the Oasis project? What's the business case like for fleets? How much savings can be had?
That's a really difficult question to ask or to answer just shooting from the hip. It much depends on the price of electricity in your local area. BC is very fortunate in that we've got the 3rd lowest electrical rates in all of North America. So that can be a real challenge for making the numbers work for solar. Other jurisdictions aren't nearly so lucky. We were doing this for research and education purposes. It does have operational benefits. The electricity generated by our installation is certainly very large. But if you were where you might make this make sense from a financial point of view is installing something like this where A, electricity is very high, and B, I think you could make it a lot more affordable. You may not necessarily need the energy storage system. The energy storage system is a fairly expensive component, and also you lose a fair amount of electricity because the batteries have a very narrow operating range to be optimal. So in the wintertime you need to heat the enclosure for the batteries, and in the summertime you need to cool it, which eats into your operational efficiency. It doesn't necessarily mean that it's a showstopper, but again, it depends on the price of electricity where you are.
Thanks, Clay. The next question is for Jeff. What can stations do without communicating with the grid?
Great. Yeah, that's a bit of an open-ended question, but I think I highlighted that there are constraints on the grid, but there are also potentially constraints within the customer's own infrastructure. So if you've got a commercial building with limited electrical panels and things like that, there's definitely an opportunity, and there are technologies available now that will allow you to manage charging between a group of stations without necessarily receiving any signals from the utility. So that's part of what we'll be demonstrating with AddEnergy's solution. They have the ability to limit power to a group of stations. And then we've also seen a few solutions that maybe on a smaller scale, for example, ChargePoint's latest dual head charging station has the ability to share a single 40 amp circuit between 2 heads. So that's a perfect example of how you can really do low-level smart charging and sort of double the amount of charging that you can do from a given amount of electrical capacity within the building. So I hope that answers the question.
Thanks, Jeff. And back over to you, Clay. How many EVs can one have before putting in a system like the one you described?
Getting all the tough questions. Well, I mean, if I go back to the that slide that I had earlier, people are asking us how many EVs can our system charge in a day, and when we crunched the numbers, it was about 50 Nissan Leafs could be charged during an average day. So again, it's a tough question to answer. The size of your fleet, how large a fleet do you need to have something like this? You don't necessarily need to have a system like this if you've got a fleet, but you really need to talk to your local utility to see if they've got the electrical capacity where you are in order to charge a large number of EVs. So yeah, I can't really shoot from the hip there. That would be a question better directed to somebody like BC Hydro or the local utility. But certainly an installation like ours would have no problem sort of charging up on the order of 50 Leafs, Nissan Leafs per day.
Great, thanks, Clay. One last question, and I'll open it up to Jeff first and then you, Clay. Are there criteria for the location of charging stations in urban areas?
So that's, again, a little bit open-ended. I guess that's a question about, electrical capacity in urban areas. I would say that one thing that we're looking at pretty closely is location of charging in residential neighborhoods. So that's obviously probably a bigger concern for a company like BC Hydro, is the fact that you have an additional, say, 5 to 15 kilowatt load on individual homes, and that might be spread out but concentrated in a few neighborhoods. And so that's definitely a challenge. But I think in the context of this discussion, probably the focus is more on commercial buildings and fleet charging. And again, that really sort of depends on the specifics of your facility and where it's located on the grid. Certainly we have seen some situations where a facility might be in a neighborhood where the utility is already sort of stretched to its capacity for, say, the given substation in that region. And so it might become difficult for a fleet to grow their grow the size of their EV fleet due to the service upgrades required. And in that case, that's where you might have to look beyond just the type of system that can do localized energy management and start to work with your utility to look at interactive demand response programs. Because there's definitely an opportunity to synchronize EV charging in a way that might not minimize your own peak demand, but might just ensure that when those EVs are charging, they're not synchronized with that substation's peak demand. And that's certainly something that we've been looking at with our parent company, BC Hydro. Yeah, definitely chime in again if I didn't address the question, and if you could be more precise.
Yeah, I'm not certain what they're referring to specifically, but Clay, if you have anything to add?
Yeah, sure. So if I understand correctly, the question is, are the recommended places in urban areas to locate charging infrastructure? And I think Jeff gave a great answer from a utility point of view. There's certainly places that don't make a whole lot of sense, and that I've seen put them in. Local municipal governments often like to put them in front of a city hall and places like that. Maybe for political reasons, but they don't necessarily make a whole lot of sense. You want to put charging stations where there's lots of vehicles. So the most obvious thing is large parking lots. If there's a large parking lot, chances are people are going to be wanting to park there that are driving electric vehicles. There's some really good work done by the TIPS lab at UBC, University of British Columbia, and TIPS lab is the Transportation Infrastructure and Public Space Lab. And they specialize in this area of figuring out exactly where in an urban area charging stations should be located. So I think they've got some pretty good answers to that question.
Great, thanks, Clay. It looks like we're coming to the end of time today, but if anyone does have more follow-up questions, please do feel free to contact us and we can send those questions along to Jeff or Clay. I just want to say again, thank you very much to both Jeff and Clay for joining us and presenting on this topic today, and thank you to all of you who attended. I'll just give the reminder that there are a number of resources around charging infrastructure specifically on the West Coast Electric Fleet Toolkit. I have the URL up in front of you there. We will have this webinar up on that site as well in a couple of days. And we'll have another webinar in June, so we'll send out a notice about that, so keep your eyes open. Thanks, everyone. Have a great day.